Word up, followers! Back at the house, recording a lecture. I'm trying to get some positive, chill reggae vibes on. Wishing I was in some tropical island somewhere instead of cooped up in my house, but you know, we're doing the best we can. Okay, so I'm recording just a pretty short lecture today because I actually have I've posted a few videos. I said I was going to do that last week. I finally did it for this week. And if you're following along in my notes, I'm actually going to deviate a little bit. And so today I'm going to be talking about, I'm just going to start with a brief introduction of approximation methods. And then I've posted a video for you to watch. It's a very short video. It's like 5 minutes. It just summarizes all of these approximation methods, which I think is more appropriate for like an advanced quantum chemistry course. And it's not my field of expertise. But so this is not in my regular notes. And then I'm also going to use this to transition into X-ray photoelectron spectroscopy, which is not in my regular notes. But there was a lot of you that did seminars last year using XPS, so it kind of motivated me to create an XPS section for this course. So this is a deviation from my notes. So this week 12, you know, maybe we'll have to make up the material, or we'll just have shortened material at the end. But in any event, focus on this video. There's two other videos I've posted, one on approximation methods and one on XPS. And that will make up the subject of this quiz. Okay. So in the approximation methods that are going to be reviewed in that other video, there's the variation method, there's the linear variation method, and then there's perturbation theory. And the book details actually all of these as well. Again, I'm not going to spend a lot of time going through them, but I do want you to watch the video summarizing these methods. But I'll highlight one example that we get from the linear variation method. Okay, and that's for the molecule HF, hydrofluoric acid, or hydrogen fluoride. And if we look at the wave functions that are created for HF, okay, then what we get is the following. We get, here, let me write down my basis set. So you can see I've got a basis set comprising H1S and F2P. And if you recall from our video last time, if I mix an H1S and an F2P, that's going to make a sigma bond. Okay? And so these terms that I call right here, these are my variation parameters. And of course, you all should hopefully recognize this H1S and F2P in the ket. Those are the wave functions of H1S and F2P. And when you go through and do this variation method, when you calculate what these variation parameters should be, you get parameters for the psi plus bonding state, and for the psi minus anti-bonding state. And for the psi plus state, for HF, you get 0.24 times the H1S wave function plus 0.97 times the F2P wave function. And for the anti-bonding state, you get 0.97 H1S minus 0.24 F2P, okay? And of course, what you get from this then, if you look at the psi plus and the psi minus state, those solutions, right, use Schrodinger equation, and you solve and get E plus and E minus, okay? And so the result of that, this is kind of similar to what you're working on in your take-home right now, right? We know the E plus state is going to look something like this, and the E minus state, the anti-bonding state, is going to look something like this. And the vertical transition goes from the minima all the way up. And that vertical transition is a result of Born-Oppenheimer, that the nuclei are relatively fixed. So if you recall, this x-axis, right, this is bond distance, and here's my energy. So, right, that vertical transition occurs at a constant radius there. Okay? And so now, let's see, I'm going to clear up some room right here. So from what you get then, from having the psi plus and the psi minus state that gives you the bonding energy and the anti-bonding energy, then that allows us to start to create this molecular orbital diagram. All right? So if we start at, let's say, some level that I'm going to call ionization. All right, this would be some threshold ionization level. And if I look at what this value of E plus is, it's going to be somewhere down here. And I know that E minus is somewhere up here, okay? And I'll call those the 1 sigma G and the 1 sigma U, right? Hopefully we recognize that, that nomenclature. And as it turns out for HF, this is about 13.4 electron volt. Okay, and let's see, I'm going to make some more room on my diagram. And then for the bonding level, okay, it's calculated to be about 17.6 EV. And again, the idea here is that from these calculations, we know where E plus is and we know where E minus is. But if we relate that to some like ionization level right up here, okay, then I get, you know, that 13.4 EV for the ionization there, and I get that 17.66 EV for that level right there. So let's redraw these with different colors to make this diagram more clear, okay? So we have that level, and then we know that this is my 17.6, and this was my 13.4, okay? And so now, well, what about, where does the F2P and the H1 exist on this? Well, we know from our calculations, we were actually able to solve the hydrogen 1s, okay? We know that that's about 13.6 electron volts, all right? So that if this is 13.4, right, then we know 13.6 is going to be, you know, maybe something like this. This is obviously not to scale, okay? So that's my H1s. And then if we do the same calculation for F2P, which we have to use an approximation method at that point because F2P being multi-electron atom, we can't solve it. But if we do some of those approximation methods, then what you find is the ionization energy of let's relabel this. H1s we know was 13.6. And so if you do this calculation for F2P, then it actually comes out to be about 17.4. So that puts it like somewhere, you know, down here, okay, for F2P. So if the E minus state for HF was 17.6, okay, F2P, just the atom, is 17.4. So that's actually how these MO diagrams get constructed. And of course, we know that one F2P electron and one H1s electron will donate to make that 1 sigma G bond. And then, of course, there's the 1 sigma U. Okay, so that's how all these things are put together. And of course, the situation becomes a lot more complicated with increasing complication in molecules. And at this point now, I think this is a really good time to transition into talking about photoelectron spectroscopy, because in photoelectron spectroscopy, what you're doing is exactly this. You're shining a really energetic light source onto a molecule, and you're ionizing an electron. And so that's how we're also able to confirm the structure and energy of these molecules and atoms. Okay, so moving along. And so if this stuff that I just talked about was really interesting for you, then, you know, going into the field of quantum chemistry and molecular modeling is a good choice for you. That's what a lot of folks in that field do. They try to calculate those types of things. And one technique that does a really good job of confirming those calculations is photoelectron spectroscopy. And now there's a couple of different flavors of photoelectron spectroscopy. I'm going to get a timeout warning here. Let me say okay. And let me say okay. Okay. So we can have UV visible photoelectron spectroscopy or X-ray photoelectron spectroscopy are the most common. And I'm going to speak about XPS, X-ray photoelectron spectroscopy, more than any of the other ones, more than the UV vis. So the way that XPS goes, you have a solid metal surface. Okay. And this is going to be an ultra high vacuum. And by ultra high vacuum, I'm talking about something like 10 to the minus 7 to 10 to the minus 9 torr vacuum pressure. So it has to be very, very low pressure. And you shine an energetic source of radiation, H nu, and of course the sample has to be electrically grounded. Okay, so I'll put that symbol in there. And if you use a really energetic source of light, if it's more energetic than is the ionization energy, which I'll call the binding energy, then an electron gets ejected. And this is our photoelectron. Okay? And so now if we look at the energy of radiation we used, H nu, that is going to be equal to what I'll call I, which would be the binding energy of the electron. So I refer back to that diagram I just drew for HF, right? That's the threshold ionization. And then now that's going to be plus 1/2 mass electron, velocity of electron squared. And that is the kinetic energy of the electron. So we have the binding energy of the electron, and we have the kinetic energy of the electron. And when H nu is exactly equal to the binding energy, then the kinetic energy of the electron equals 0, and thus no photoionization can occur. Okay, so we call that threshold ionization. So what we really need is for H nu to be greater than the binding energy, because then the kinetic energy of the ejected electron will be greater than 0, and that will allow the electron to fly off the surface. And that's actually what is detected in this technique. It's not the light that's detected in this technique, it's the ejected electron. Okay? And so the way that works here is if we have, so here's my solid surface, okay, grounded. And then we typically have some really high energy light source, which I'll talk about in a moment, H nu. And then our electron gets ejected, and typically this goes into what's called a hemispherical energy analyzer. So it's hemispherical, so it's like half a sphere. And down here would be the detector. I usually draw little like eyeballs for the detector. And there's a series of magnets in this that will allow the fastest electrons to make it all the way over to this side. So I'll say fast. And the slowest electrons won't bend as much, so they'll make it down to this side. Slow. And that's how those electrons are discriminated against in their energy. So what this means is if you use a constant energy source, which is typical. So I'll write down typically you use, let's see, where did I put that information? So I'll write them down, and I think I have it in another document. So typically we use the magnesium K alpha line or the aluminum K alpha line. And if you recall from our spectroscopic notation, the K shell, right, that refers to the 1s core level. Oh wait, actually I think I have it over here really quick. Well, it's something like, I'm just going to guess, it's something like 1200 electron volts, and the aluminum K alpha is something like, I think it's 1456 electron volts. So that's a really high energy. That's an X-ray, right? 1456 electron volts. So when you're using a constant energy right here, all right, and you have multiple, you have different samples that are going to have different ionization energies, different molecules or different atoms, you're going to have different kinetic energies of electrons, okay? And so what the technique then does, it determines the kinetic energy of the electron, and it says kinetic energy of the electron minus the energy of radiation used, and that's going to equal the binding energy of the sample, okay? So that means with a constant h nu, Ke varies, and thus you're able to see a variance of Be. Okay? And so what I want you to do at this point is probably natural to pause this video, watch the little short video that I gave you in XPS. That's going to give you some cool animations and all kinds of stuff. And then I'm just going to pick up on a few things that I felt like that video left out. And so one of the main things that I want to talk about that's characteristic in XPS is spin orbit splitting. Okay, so I'm going to go to this document over here. I'm going to make this a little bit smaller. And this is a PDF that I've loaded up in the notes. I think this is a nice summary of XPS in addition to the video that I'm going to post, the short video. So I would review through this. It's kind of long, but there's lots of nice pictures. So here we can see this is a photoelectron spectrum of titanium oxide. And now what they're showing you on the x-axis here is the kinetic energy of the ejected electron. That's okay to show it like that, but typically what you see on the x-axis is the binding energy of the photoelectron. So this is a picture of a typical XPS. These things are usually gigantic. There's lots of vacuum pumps. This is the hemispherical energy analyzer. That's that X-ray source. And the machinery involved in an XPS instrument is really impressive. I would just go do Google images on XPS, X-ray photoelectron spectrometers. They are impressive. I mean, they take up an entire room. They're crazy expensive, but they're really, really cool. Really cool to look at, too. So I'm going to keep going here. Let's see. Sorry, one moment. Okay. I feel like I've lost a page in my notes. And I'm recording, and I'm not stopping. Oh, yes. I found my page. Here it is. Oh, yeah, okay. So the magnesium K alpha was 1253, and the aluminum K alpha was 1486. So they're pretty large energies, okay? And so I knew this is why I was off, because I lost a page. So I first want to talk about primary photoelectron spectra, okay, such as XPS. And if, for example, maybe suppose this was the potassium 1s level, and then here I have 2s, and here I have 2p, okay? And so I'm going to go ahead and populate this, And you'll see why in a minute I didn't finish that 1s level. So with XPS, it's a core electron technique. So you can see in this picture right here, we're knocking out core electrons, K-shell electrons, all right? So that K-shell electron, that creates a hole, and that photoelectron gets ejected, right? So that's a primary photoelectron spectra. We can get into secondary photoelectron spectra via the following. So now what we have here is we have a hole. We have an open vacancy, all right? And if I look at now this 2s level and 2p level, so let's go ahead and populate it up. So now what could actually happen with this level is we can get the relaxation of an electron back down to this core level, which is shown right here, okay? And as it turns out, that would emit a lot of energy. That process would actually emit an X-ray. And so what that can do is now create a secondary ionization, okay, where now, or similarly, I'm also showing that this could occur, and that second photon could now eject another photoelectron, a secondary ejection. And that's called the Auger electron. So that's A-U-G-E-R. It's French. It's Auger. It's not auger. Okay. And so I'm just going to focus on our primary photoelectron, XPS. Secondary photoelectron techniques get rather complicated to understand and analyze. So we're not going to worry about that level. Okay. But let's keep going with this, and there's a good summary. If you keep reading through this, it talks about like why you have this inelastic background, which is interesting. I'm not going to really go over that too much, but what I do want to go over are this spin orbit splitting, as you can see from this document right here. Okay, and so typically XPS doesn't quite use the full proper atomic term symbol notation. They typically use this notation that you see right here, where they note N, they note L, and they note J. And the level J is quite important in XPS. So for example, let's talk about copper, okay? We know copper is 3d10 4s1. Technically, the 3d10 is lower in energy, okay? That is a doublet S 1/2 state. And if you look at its photoelectron spectroscopy, typically in copper, the 2p level can get excited, or the 2p level is ionized. And if we recall, my 2p level is split by J 1/2 and J 3/2. And it's important to note, even though copper has a full 2p configuration, we have to remember that we're creating a hole and we're ejecting that electron. And we could have ejected either the downspin electron or the upspin electron, either one. And that's why we have this 1/2, 3/2. And if you remember here, if this is my threshold ionization, and we recall the downspin, the J 1/2 electron is always lower in energy, what that means is the 1/2 state is actually going to have a higher binding energy than the 3/2 state. And also the difference is what creates the spin orbit coupling level. And you can see right here on this document, I've got a photoelectron spectroscopy of the copper 2p level, and you can see that's a difference of 19.8 eV. And that's something we use in XPS as a characteristic diagnostic if you were doing an unknown analysis. Suppose you were analyzing some material and you didn't know that it had copper in it. Well, if you would see these two peaks corresponding to 2p 1/2 and 2p 3/2 with an energy difference between 19.8, then you know that it has to be copper. And also, The lower, you can see I've got a bunch of other things up here. I've got silver 3D and gold 4F. The lower J state is always lower in intensity. So that's one way that you know what you're dealing with. Okay, so this would be the 2p 1/2 and the 2p 3/2. And also, like I said, that binding energy gives you characteristic difference for a given material. And if you wanted to know what it was, you would typically look it up, use the literature value. It's fairly complicated to calculate this binding energy difference. So we typically rely on literature or spectra. So now you also notice here there's this copper 1s signal, and it's not split into the two levels. And that's because you see this document right here, for L equals 0, S levels are singlets, no splitting. But for L is greater than 0, PDF levels give rise to doublets because the unpaired electron left in an orbital can have its spin and orbital angular momentum either parallel or anti-parallel. Again, that's the up-spin electron or the down-spin electron. Okay. So, and then you can see binding energy of J value in doublet is always higher. So binding energy of 2p 1/2 is always greater than 3/2 because of this right here. All right. And then finally, the magnitude of spin orbit splitting increases with Z. So the bigger the nuclear charge, the bigger this splitting will be. However, there's an opposite effect that happens when you have an increased distance from the nucleus. So the magnitude of spin orbit splitting decreases with distance from the nucleus. So here's some examples. If I compare copper 2p to silver 3d to gold 4f, if we were looking at the 2p levels for all of those, and keep track of the periodic table, right? It goes copper, silver, gold, right? Down the row. And so then you would expect, if we were looking at the 2p level of all of these, that binding energy would increase. And it would if we were looking at the 2p level. However, because here now we're seeing P, D, and F, that's related to this point right here, the magnitude, having to do with increased nuclear shielding. So as we go from P to D to F, we're getting further away from the nucleus, so that spin orbit splitting decreases. So that's another characteristic way of telling if you're predominantly dealing with the P level or the D level or the F level. The F level typically gets really close, but the D and the P levels are further apart. And the last thing that I want to say about XPS is the effect of oxidation states. So if you imagine here my carbon 1s level, for let's say graphitic carbon, you know, we'd have a level right there. But if let's suppose I had a carbonyl, right, a carbon-oxygen double bond, it would have a different level. Or if I had a carbon-carbon 1s bond, it would have a different level. Okay, and so as an example in this document right here, so here you can see is the carbon 1s spectrum of citric acid. And so citric acid is going to have several different carbon oxidation states. And as a result, in the carbon 1s region, you get, like, you know, the carboxylic carbon, you get the alcoholic carbon, you get the aliphatic carbon. So just like is observed in FTIR, you would get different binding energies for the different oxidation states. And using the process of deconvolution is how you would do that. So fitting the spectra to multiple peaks, that's called deconvolution. And that is the subject of your Spectroscopy 1 assignment, which is now available for you to do. And then the last thing I'll say, you can see a really good example of differing oxidation states with sulfur, right? If I look at here, sulfur fluoride, or excuse me, silicon fluoride, silicon difluoride, silicon trifluoride, and silicon tetrafluoride, you can see when you look at the different oxidation states of the silicon, there's a core level shift in those ionization energies, and you can see you would get multiple peaks corresponding to that. So if you're analyzing something like citric acid in XPS, something that has a really complicated spectrum, you typically would also need to do the FTIR spectrum at the same time. And for those of you that have done a lot of that literature search for your seminar project, you might have noticed that people often will do XPS and FTIR at the same time because the FTIR can help you assign the different functional groups. Okay, folks, so that's really all that I'm going to record for this week. So please watch those other 2 videos that are in this module, and the quiz that I create will be based on these 3 videos. So this video and the other 2 videos that I've posted. And then, like I said, the Spec 1 assignment is available. And so now that we've talked about XPS, that's going to help you do the Spec 1 assignment. I'm totally happy to help you out with that. So I hope you're staying on top of it. I know I've just released a bunch of stuff for you to do. There's a take-home exam. You know, these quizzes and assignments are rolling out. But now that I've created Spec 1, all of your homework assignments, your tutorials, they're all available. You can now do Spec 1, Spec 2, and Spec 3. We'll have take-home exam 4. So we're kind of like, and that's going to come at the very end. So we're kind of getting kind of close to the end, even though it doesn't feel like it. So I hope you're just keeping up with things, and don't hesitate to chime in to office hour anytime you need some help. Okay, folks? I will see you later.